So today I will be talking about data representations. So we have basically talked quite a bit about the different methods for doing machine learning and data mining. Now I will kind of take a step back and focus more on what do you actually need to do in order to go from a practical real-world problem that you might have into something that you can feed into those machine learning algorithms, because it's not quite as obvious as you would imagine. So if we take a simple example problem, one popular one is cell phone churning. So this is basically when customers of cell phones switch companies every year or every couple of years to get slightly better rate or whatever. And the challenge here is that for telecommunication companies, this is expensive. Right? It's more expensive to acquire a new customer than to retain the one that you currently have. It requires changes network configuration. You usually have more support questions from new customers, things like that. So this is the kind of behavior that you would like to discourage. You would want people to stay more loyal to a particular network. And the most obvious way of doing something like this is to offer customers a discount. Right? So you want to say, well, okay, if you stick with us for another year, we will give you 10, 20, 50% discount on the services. And then if you think about this clearly, if you can actually prevent this kind of churn, you will probably save some money. So if you give a discount to a customer and that customer decides not to leave your network because of this discount, that's a good choice. You made some money. The challenge is, of course, that if you give this kind of discount to somebody who was not planning to leave the network, you are just wasting the money because you are giving away discounts for no good reason. So very clearly, this is a prediction problem. Right? If you can use machine learning to predict who is going to churn, who is not, you can get some kind of benefit. So the question then becomes, in this kind of setting, what really should be your prediction task? And on one hand, it seems to be quite obvious. You want to predict churn. But then if you start thinking about it in more specific terms, the most basic prediction you could do is just yes or no. Like, will this customer churn or not? But then you can start thinking deeper and you can try to make this prediction task more complicated. For example, you can ask a question of when will a customer churn. Right? If you can know exactly when they are going to switch the network, then you can make better decisions about how to keep them. Even better would be if you can actually predict what is the minimum discount that you need to give this customer to keep them in the network. If you just predict whether a customer will leave or not, then you need to have an experienced salesperson who will decide what kind of incentive to offer to this particular person. Instead, preferably, you would want this to be solved by machine learning as well. Even better would be to predict the possible future profit that this customer can give you. The question is it even worth keeping this customer? If their future profit is not really big enough, then maybe the effort of keeping them is not quite worth it, and so on. So basically, you can phrase this prediction task in many different ways. And on some level, this boils down to a different kind of trade-off between how difficult the prediction task becomes and how useful it is for future decision support. If you think of it, almost never you make decisions in the vacuum. That there is almost always kind of chains of decisions. Like in here, we are talking about the customer is likely to leave the network for your competitor. If you can know this, then the next step is, okay, so now we want to keep this customer. How do we keep this customer? We give them discount. How big of a discount? And so on. So the question is, which part of this kind of decision chain you want to replace with machine learning, and which part you want to leave as something that salesperson or somebody else will do. Right? Ultimately, you would want to replace as much as possible, because that makes the rest of the work as easy as possible. But then you want to find the right balance between what can be automated and what should stay, or what should you keep as a kind of expert decisions. So that's one side of this kind of when you try to formulate machine learning or try to formulate real world problem as a machine learning problem, the scope of this in a sense. The other side of it is also what kind of training data you have. In the telecommunication setting, you would say, okay, let's say that we work with the telecommunication company and they give us X years of customer data with labels, so telling us who churned or who switched network when and so on. The question, of course, becomes, what does it really mean, customer data? Because customer data can be a lot of different things. The most kind of obvious case you can think of is basically history of all the calls and messages that the customer made. That's quite simple. But what you can actually do is you can imagine at least getting quite a bit more. So for example, you could have a graph of the social network, because if you know that I'm calling a particular person and that person is calling somebody else, you can build a social network on top of it. You can figure out who knows whom, and you can make decisions based on who is the kind of influencer in this network and so on. Also, in addition to just the calls, you have quite a bit more information. For example, you could imagine taking advantage of the location during the calls. You know when the person is when they are making the call. In fact, you know where a person is even when they are not making a call. Is that part of customer data?
Sorry, is this even legal?
Well, that depends on a number of different things. It's definitely legal to collect this information because the network has to collect it in order to do the service, right? They not necessarily need to know the exact location, but at the very least they know to which base station you are connected when you are doing your calls. So they might not know your location with the couple of meters accuracy, but they know in which city you are. Now, whether it is legal for them to use this information for making those kinds of predictions or not, that's a different question. I'm not going to answer that. That obviously depends on what kind of agreement you have signed with your network.
I see where you're going. I understand it fully. It's interesting the use case here.
Mm-hmm. Yeah, but that's why it's so interesting, because obviously when you start thinking about it, yes, cell network needs to have information about the calls you make, but they actually could have a lot more information than you think at the beginning, right? I mean, in principle, they listen to all of your calls. This customer data which they use could include everything that you say. That would probably be illegal, right? That really shouldn't happen. But you have no way of really knowing if they do it or not. Right? Then the question is, can they connect the data from the network itself with some other information? Like, do they know how much you earn? Do they know what education you have? Do they know what kind of hobbies you have? And so on. Potentially, all of this information could be useful in predicting whether you are going to change your network or not. So even kind of on higher level of abstraction would be, do they know if you are satisfied with the current service level or not? That would be very useful feature to have when trying to predict who is going to switch to another network. So all of those things are important in figuring out what you actually what do you expect the accuracy, for example, to be. Obviously, the more information you have, the better it can be. So it's important to understand what is available, what isn't available, what is legal, ethical, and so on. All of those things are very important in figuring out what you want to do. But then when you try to formulate this as a machine learning task, this basically becomes two sides of a coin. On one hand, you want to define the action space. So you want to define what is your instance or example, and then for this instance, what kind of decision do you want to be making? For example, again, coming back to this churn thing, seems quite easy to say that you are talking about a customer, but it's not necessarily that obvious what a customer would mean. It could be a single person, a single phone number, but maybe it's a whole family or a whole company. There might be or phone numbers which are owned by the same customer, and if they are going to switch to a different network, it will actually be more than one phone number. How do you figure that one out? Right? Those are all kind of interesting questions. And then, as I said, what kind of prediction do you make? Do you just decide, is the person going to leave or not? When, why, all of those things. And then the other side of it is, how are you going to represent your data? So the information you have about the customer. And that is both what types of information you have, but also how to represent it, meaning in what way to store and process it. So obviously, what data is available is important, right? If you don't have location information, that's something that you need to kind of take into account, and you either have it or not. If you don't have it, you can try to reconstruct it based on some other potential features. If you have it, then the question is, what is the granularity of it, and so on. But then, even for the data which you do have, the question is how to turn this kind of, let's call it raw data, into useful features. And this is mostly what this lecture will be about. So basically, how to take the information that you have available and present it in a way which makes it useful for machine learning.
What is the definition of feature in this?
So basically here, when I'm talking about features, I'm mostly talking about the kind of tabular representation where you have examples as rows and attributes or features as columns for the data. So that's not the only possible way, but here I will be mostly talking about that. So that's basically the situation where you might have some kind of structured information about your instances, but then you want to capture the features as kind of atomic, mostly numbers.
So in this example with the phone calls, what could be a feature then, for example?
Mm-hmm. So I will come back to some of those.
Yeah.
Mm-hmm. So then there are kind of two sides of looking at those features. One is how to create more features, so how to turn data that you have into useful form, and the other one is some of the data that you have not really relevant? Can it be removed either to save space or time, or to just not confuse the model, right? So what data can you remove? What data can you add? How would you transform the features to make them more useful? Those are kind of the topics that I will be talking about. So now to talk about some more concrete examples. If we talk about the telecommunication data, let's say we ignore all the kind of privacy issues, so there is no location data, there is no transcript of calls, we only have the log of cell phone calls. So let's say we have timestamp, the phone number that you called, how long the call lasted, and maybe signal strength. So this is clearly the kind of information that a network company would store anyway, just kind of to make sure that they are providing good service. And then the question is, if they want to use something like this for churn detection, how would it work? So the first question is, of course, is this a good kind of representation? Now, just kind of to take a step back, let's imagine that we want to do machine learning using decision trees. Right? So here is an example of how a decision tree looks like. We have talked about this, so I'm sure it's nothing new. Decision tree, you have those conditions in each of the nodes that decide you whether to go left or right until you finally reach a decision. So if you think about this kind of log representation of data, what kind of conditions you could have in a decision tree? A condition could be something like, did the customer make a call on 18th of August 2018? If you have data in terms of the logs of all the calls, you can very easily check if the customer made a call or not, right? Or you could have, did the customer ever call a particular number? Or you could have, is there a call that lasted more than 15 minutes? And you have call durations. All of those things are easy to do. You could build a decision tree with something like this. The problem is if you start thinking about those kinds of decision nodes, they don't seem very good, right? Because it really, if I'm going to decide if I want to go to a different network or not, no single call is really informative enough. What you really want to do is you want to be doing some kind of aggregation of this information and then make decisions on the kind of higher level behavior of the customers. So here you can kind of clearly see that even though you have this information which in principle contains all the relevant data, it's not very easy to use this data directly in something like machine learning using decision trees. So instead, what you would want to do is you would want to transform this list of all the calls that I have made into some kind of more abstract, more aggregated features. For example, average call length, number of calls per day, and things like that. Those would be better features to then build a decision tree and make decisions on. So basically, kind of on one extreme way of looking at it, what you want is you want to have features which are informative in a sense of features that allow you to make clear distinctions between the classes that you are interested in, right? And you can visualize it using something like this. Let's say that you have two types of customers, the circles and the stars, and you want to separate between them. Here, obviously, feature X1 is a pretty good feature. If X1 is smaller than 0, you are almost certainly a circle. If it's bigger than 0, you are almost certainly a star. So those are the kinds of features that you would like to build. Now, of course, if it was easy, we wouldn't be talking about machine learning, because if you have features like this, then you don't really need machine learning. So in practice, what you want to do is you want to get close to features like this, but you will not really be able to do it in practical cases. So what instead you do is you try to find features which are informative together. Generally, as I said, it's hard to find an individual feature which is very good, but you can find combinations of features which are good. So here, for example, neither X1 nor X2 by itself is very good, right? You cannot make decisions whether somebody is a circle or a star based on any single of those features, but together they allow you to make those decisions very well. And of course, again, we can easily visualize things like that for 2 features, maybe 3 in 3D space. Once we start talking about combinations of more features, then people are not very good at finding those. Computers are much better. So this is kind of the whole area of machine learning where the main strengths goes. It allows you to find large sets of features that in combination give you good performance. But ultimately, somewhere at the bottom, it still is about features that capture some of the important things. Because there is obviously no guarantee that 2 features will be useful. And here's an example of features which are useless by themselves and equally useless together. So even if you have both of them, you cannot make particularly good distinctions between stars and circles. Okay. The problem that kind of you see is that even if you have a feature which seems useless, it might turn into a non-useless feature if you add something to it. So it's generally quite difficult to kind of a priori decide if a particular feature is good or not. And here is another example of a very kind of the most extreme case of it. You have two features, x1 and x2, which individually they are completely useless. They don't allow you to do any kind of classification at all. They have equal, if you try to use them to classify, you will always have 50% error rate, because then the number of circles and stars is equal in each of those squares. But together, they allow you to do perfect classification. Now, again, this is kind of an extreme case. This is a toy example. It just visualizes the principle. In practice, it's usually not quite that simple. But that's the main point I'm trying to make here, is that if you are looking at a single feature individually, it's really not possible to tell if it can be useful or not in combination with something else. So one of the important things is that you really want to use your domain knowledge in trying to come up with such features.
Just a question about the figure here. The rings and stars to the left of the x2 axis, is there some kind of aggregation of how many there are on a line, or a specific x2 value? Or?
Yes. So the stars and circles outside the axis, this is just a projection of the data on this particular axis.
So the more ink, the more stars, for example. So if it's almost black, there are many stars.
Yes. Yeah. There is just an overlap of several. Mm-hmm. Mm-hmm. So basically, one way of looking at the features kind of individually is to start talking about relevance of features. And there are different definitions of relevance. You can define it in probabilistic terms. But what you want to do is distinguish between strongly and weakly relevant features. So basically, strongly relevant feature is a feature which contains information that no other feature captures. So this is kind of a feature that you cannot do as well without as you can with it. And then a weakly relevant feature is a feature that either contains information that some other features also contain. So you can either pick feature A or feature B. They would capture the same information, or it contains information only if combined with other features. So by itself, it's not really useful, but when combined with other features, it allows you to get more information. Right? And then, of course, you have features, or you can have features which are completely irrelevant. But that's still not exactly the same as the notion of probabilistic independence. And so here again is the same example as before. You have the XOR case where you have two different features. Each of those is useless by themselves, but quite informative when you bring them together. Here is another example of weakly relevant features. You have two features which are correlated. Okay, different colors correspond to different classes. By themselves, the features are useless, but together, the features allow you to do good classification. And the thing is, you can formalize this notion using the notion of conditional probability. And so then you would say that strongly relevant feature is feature xi, which is not conditionally independent of y, given other features. So basically, any feature which for which you can say that it is not independent from the decision class that you want to that you make, even given all the other features, that would be strongly relevant feature, because that means that even if you take into account all the information from other features, there is still something new that this feature xi brings to the table. On the other hand, the weakly relevant feature is defined in a similar way, also using conditional independence, but this time it's only for a subset of other features. So feature xi is not conditionally independent of the decision class given a subset of features, but it would be independent given all the other features, right? And this corresponds to, as I said, this notion of either there is some other feature which captures the same information, or the information from feature xi only becomes useful when combined with some other feature. And this is important in a sense of that allows us to talk about the formal definition of feature relevance. The challenge here is that it really doesn't capture everything that we are interested in, because it turns out that using this probabilistic definition of relevance, you can still have strongly relevant variables which are useless for making classifications. So here is one example of how it could look like. Both x1 and x2 are strongly relevant in a sense of the probability of being blue or red class changes as you change the value of both x1 and x2. But because of this kind of noise in the blue area, you still cannot make meaningful classification based on those two features. This is a little bit counterintuitive in a sense, but what you notice is that just because a probability of a particular class changes doesn't really allow you to always make decisions, because you still can have the noise which really makes it impossible to make individual decisions on individual data points. So what you can still do is you can use this notion of relevance in order to select the features which are most useful, right? So you can do either forward or backward selection. So imagine that you have some number of features and you want to figure out which ones are most useful. You can start with the empty set and then keep adding features as long as you will get, as long as you can find more features which are relevant. And this kind of procedure is guaranteed to find all strongly relevant features, but it might miss some weakly relevant ones because you are adding one after another. So if you have this kind of XOR example, you will never add the first of those variables because it will never seem useful. If you would have the first one, then adding the second would be clearly useful. But if you never add the first one, you will never notice that the two together are actually helpful. Or what you can do is you can do the backward selection, where you start from the set of all features, and then you incrementally remove features one after another, as long as the ones you are removing doesn't make the resulting feature set conditionally independent from the decision class. And again, this way you are guaranteed to keep all the strongly relevant features, but you might, by mistake, eliminate some weakly relevant ones. And the challenge here is that if you really want to find the best possible set of all relevant features, this is an NP difficult problem. Right? So you basically would need to do an exhaustive search through all the possibilities, and that's expensive. There is a lot of such subsets, so you cannot really do this in an exhaustive way. Otherwise, you have to live with those kinds of greedy procedures when you do it one by one, but then you risk the fact of finding the suboptimal solution. Or you could do any other kind of approximate optimization procedure, of course. The other side of it is feature engineering. So this is basically, the feature selection is if you have some number of features and you want to remove the ones which are not needed. The other side of the coin, obviously, is when you want to add some more features. And the general idea here is that when you have your initial data set, usually this corresponds to some kind of domain knowledge, but it's mostly focusing on storing the data, not really analyzing it. And when you start your machine learning project, people will give you data in whatever form they have used in the database or whatever for storing it. The main purpose was making sure that the data is remembered, not really optimized for analyzing it. So one example would be if you talk about images, the most common way is obviously store them by pixels. And pixels are not a very good way of analyzing images. Any single pixel doesn't really contain much useful information about the image itself. So typically what you want to do is you want to take this data that you have and then try to build more features, generally based on past experience with this particular domain. And so trying to capture different aspects of information that the experts consider important. And the most common way of doing it is to try to capture how people make decisions. And in most cases, you are using machine learning to try to reproduce human decisions. So you are trying to make sure that all the information that people take into account when making their decisions will be represented in those kinds of features. So if we talk about images, this could be, for example, different contours or different textures in the images. Those are much better features than individual pixels for understanding what's in it. Similarly, for natural language processing, you could talk about different grammatical clauses. You don't want to talk about individual letters. You want to talk about, okay, this is one part of a sentence, this is another part of the sentence, this is a verb, this is adjective, and so on. And then, in addition to kind of building new features from raw data, you can also combine existing features. The challenge here, of course, is that when you talk about removing features, when you talk about feature selection, we said this is difficult and incomplete problem, which means exponential complexity. When we are talking about feature engineering, so adding new features, now we are actually talking about infinite number of possibilities. And if you have some kind of data, you can always create infinitely many new features. So you cannot do it exhaustively either. You need to do it in some kind of meaningful way. But if you think about feature engineering as a process, you can think of it as a way of transforming raw data. So you have some kind of information that you want to transform into features, so into generally numbers. But the point is you want it to better represent the underlying problem. So you want your features to correspond to the interesting aspects of the problem you are describing in a better way than the raw data you had before. So that the predictive models you build will focus on the aspects that are important rather than just kind of the noise in the raw data. And the point is always to improve model accuracy on unseen data. So this is kind of the definition of what feature engineering is about. And on one hand, there is an interesting tension in, let's say, machine learning research area between feature engineering and algorithm development, in a sense of the main idea behind machine learning is that it should be able to learn from whatever representation of data you give it. The less feature engineering you need to do, the better the machine learning algorithm is. On the other hand, if you have a difficult practical problem, generally machine learning algorithms are not really good enough to do all the work. So you want to help them in a sense by giving them better features. So if you want to solve practical problems, it's generally much more worthwhile to put time and effort into designing better features rather than into designing better algorithms. Right? And this is something that's quite common in if you have, for example, those machine learning data mining competitions like Kaggle and so on. Most of people who participate in those competitions will use state-of-the-art algorithms and put most of their work into engineering the features which are well suited for a particular problem. So from my perspective as a machine learning researcher, I'm always interested in developing better algorithms. But from a perspective of somebody who wants to actually solve a particular problem, most of the effort probably should go into feature engineering. So if we think about what kind of features would be useful for different types of problems, imagine that you want to recognize a chair from an image. What kind of features can you think of that would be useful for doing that?
The number of contact points to the floor.
The number of, if you can detect the floor, then you could find the number of contact points. Yes. Mm-hmm.
Maybe material.
You could probably do something with material or texture. Mm-hmm.
Form, or like try to detect these squares and stuff like that.
Yeah, there probably should be something flat to sit on, although some of those artistic chairs probably don't have it very well. If you have a person sitting on it, that would be a good indicator that it's a chair, and so on, right? So there is a number of different things you can try to do. If you would try to recognize autism in children, for example, here we could take existing medical knowledge, right? If you go to different kinds of medical textbooks, we could find rules for deciding whether somebody has autism or not. The problem is those rules are quite complicated. And here is one example of what you could do. Those kinds of things are pretty much impossible to automatize. And like impairment in use of multiple nonverbal behaviors such as eye-to-eye gaze, facial expression, body postures. There is basically no way you could automatically decide whether a person has impairment in eye-to-eye gaze. So you could try to create proxies for different things. You could consider those the diagnostic described here as some kind of a guideline, and you can try to look at different hints. For example, this tells you that eye-to-eye behavior is important. That means you might want to do some kind of gaze detection and try to base your predictions on that. And so there are some hints in here that you could use, but you probably couldn't just implement this directly. Something, well, maybe simpler, right? Just imagine a very, very toy problem of recognizing a prime number. And so 2 is prime, 3 is prime, 4 is not prime. How would you imagine features for doing that? That seems quite difficult. Like, if you don't know what a prime number is, it feels pretty much impossible to use machine learning to figure out something like this, right? But what kind of features you could do? So forget what you know about primality. You have those 15 examples here. What kind of features you could imagine?
Couldn't you maybe try to divide by some other number and then see if that number is even or not, or something like that? Like try some mathematical operations and create a lot of different things there. Maybe shoot a little broad and then see if something sticks.
Mm-hmm. Yeah, checking if a number is even or odd, that seems like a good start, right? That gives you roughly 50% accuracy. Anything else? Yeah, seems hard, right? There is basically, I mean, the notion of primarity is quite simple conceptually, but the challenge is this notion is really not visible in the representation of the numbers that you see here. Right? The digits themselves don't really tell you much about the primality. So it seems very difficult to design good features for something like this. You can come up with features which will either over or underestimate. Again, you could say being even or odd is one thing, and then you say, well, even numbers are generally not prime, and then you would be, you would almost never make mistakes there. And then it turns out that there's a lot of odd numbers which are prime, so here you would make a lot more mistakes. But that's one kind of common example of something that you might notice, that there are some features, or that in many realistic problems, you can have features which are quite representative or which explain the behavior of a particular type of objects quite well, but then there are other types which are not covered by your features. And so again, the even versus odd feature is very, very good for detecting non-prime numbers, because half of the non-prime numbers you will be able to classify correctly using just this one feature. It's not very good for detecting prime numbers. So this is important thing to make sure that your features are kind of covering all the possible cases, and that's one of the challenges. So taking another example, if we want to detect email addresses, so we have a string and we want to say, is this an email address or not? Right? Task seems quite simple. So then what we could do is we could try to build a number of features based on our domain knowledge of what an email address could be. So let's say we have abc@gmail.com. We can create a number of features like this. You could say, okay, is the length bigger than 10 or not? What the fraction of letters to other characters? Does the string contain the character? Does it end with com or org or something else? And we can do this, and again, with good enough features, we can probably learn what is an email address quite well. If we have too few features or not really expressive enough, then quite clearly we will not be able to make a good learning. Now the problem here, of course, is that this is very ad hoc. We have, for example, this ends with com. Why specifically com? Right? Why org that there is a lot of other possible endings that could be quite interesting as well. So generally, when you are trying to build features, instead of building individual features, you should rather talk about different kind of templates, because it's hard to know, for example, in this email address case, which suffixes are really relevant. I mean, .com and .org are obvious, but there is a whole bunch of them. So you probably will not really know all the relevant ones. So instead, what you want to do is you want to include a whole bunch of different features and then let machine learning algorithms pick the ones that are most useful. And kind of the idea behind this is that people are good at coming up with abstract concepts, right? You can say, well, the end of the email address could be important, but we are not necessarily so good with coming up with exact details of, okay, let's list all the possible endings of email addresses and see how, or what was the probability that for every ending, this is an email address versus not. That probability no human can really give you. This is kind of the information that the machine learning will be much better at. So one solution is to say, well, let's just add a whole bunch of features. Does the email address end with AAA? Or does it end with AAB? Or does it end with ZZZ? And then we'll have all of those features, and then the machine learning will learn which of those features are indications of email addresses, which are indications of other types of strings. Another example, if we want to do, for example, context-sensitive spelling. So if we want to fix the two mistakes in spelling of a sentence like this, again, we could have as our output space either the entire vocabulary, so basically all the possible words, or we could just try to focus on the words which are often confused. And the second one would, of course, be much easier, but would be much, or would be less useful in a sense of it will only help you when you make those particular mistakes. It would ignore all the other mistakes. Right? You could have this model as a multi-class classification where you try to predict what is the particular class that you have. And then you would still need to define the feature space. So how do you represent a sentence for your for the model, right? So here we could have a number of different features. An example would be we can have different kinds of relations in this sentence. So we can have the text itself, we could have the order of the words, we could have different kinds of properties, for example, from where this text comes. And then you want to define functions based on those things that will tell you, that will help you differentiate between different sentences. So for example, if you want to figure out if you should use the word piece or piece, how you could do it? You could build a number of features. For example, does birthday appear within window of 3 words? Does cake appear within a window of 3 words? Is the preceding word a verb? So now we would have 3 different features. For any sentence, we could calculate the values of those 3 features. All of those are just binary. So sentence 1 would be represented as 0, 1, 0. Sentence 2 would be 0, 0, 1. If you visualize it graphically, it would be like this. And then you could learn which type of piece should be in different kind of sentences based on different combinations of features. That's kind of the general idea behind feature extraction. And then the most common way of building such features is to focus on predicate features. So predicate features are just features which give you true or false output. That's of course not the only possibility. You can have any kind of value. You can have continuous numbers as your output. But in many cases, it turns out that it's natural for people to talk about predicate features because that's how we think about the world. We talk about the world in terms of different kind of categories, right? So we are trying to capture concepts of interest based on our domain knowledge. So we could imagine things like is subject sleeping, is subject driving as different kind of features that we can then calculate from the raw data in a quite meaningful way. The challenge, as I mentioned, with features which are not binary is that it's hard for people to really decide what the values should be. Right? If you are trying to say how well a particular person is driving, is it a good driver or bad driver on a scale from 0 to 100, that's a difficult task, that there's a lot of subjectivity in it. It's generally much easier for people to talk about kind of sharp concepts, either somebody is driving or not. The other advantage of predicate features is they are also very easy to combine, because if they are represented as 0 and 1, then if you want to combine them by the AND operator, you just multiply them. If you want to have OR, then you just sum them up. The challenge with those kinds of representations is that in many domains, you will use a lot of different predicate features. So we'll have thousands of, or even millions of those. Right? We talked about this 3-letter endings of email addresses. There is a whole bunch of possibilities there. So that means that the dimensionality of the data you end up with is generally very high. And in many cases, most of the features will not really be active for an example. So what you will end up with is a sparse vector, a vector with a lot of zeros and very few ones. So then you can compress it. So it's not the space that's the challenge, because you can compress it to just store the true values. But the problem with analyzing the sparse data like this is that in high-dimensional sparse spaces, all the data points are virtually equally distant from each other. So basically, if you imagine those examples like S1 and S2 here, there are so many that there is a lot of zeros in those vectors and just a few ones, which means that the probability that two different vectors will have one in the same place is quite low. And that basically means that the distance between 2 points becomes just the number of ones in each of those. Doesn't matter in which position the ones occur. It's only how many ones there are. Right? If you take this S1 example, the distance between S1 and S2, I mean, of course, depending how you measure the distance, but if you just measure it as number of the differences, the distance between those two vectors would be 4. There are 4 positions on which those two vectors differ. But then if you imagine a different vector S2, which would be, for example, 5, 7 instead of 4, 7, the distance from S1 to this new vector is also 4. And the distance from S1 to 9, 7 is also 4. So basically, almost all the vectors will have the same kind of distances, which makes it very difficult for machine learning to find similarities, to find groups of objects which are similar to themselves and different from others. So it's not impossible to learn from data like this, but it's definitely a challenge when designing those kinds of features. Right? And when you talk about sparsity, there are two different types of sparsity, which are both kind of problematic. So one case is when you have a sparse function space, which means that you have highly dimensional data, but your actual output, your decision, only depends on very few of the features. So you have many irrelevant features. And the challenge here is that it's difficult for machine learning model to figure out which of those features are actually useful and which ones are just noise. If you have enough of this noise and not that many training examples, the noise will seem equally interesting as the real underlying patterns. And the other side of it is the sparse example space, where you have highly dimensional data, where only few features are active in each example, so just as we've shown before. And the challenge here is, of course, that because so many examples are so similar, it's difficult to find the interesting patterns in it. And for example, natural language processing is the case, is the example domain in which we have a lot of both of those types of problems. So there, we would be looking for different kinds of dense embeddings. I will come back to this a bit later. But if we come back to this topic of feature templates, so what we want to design is, based on the domain knowledge, we want to design sets of features instead of individual features. So what we want to do is we want to use domain knowledge to identify those kinds of templates, the general rules that encode relevant information, without specifying too many details. And as I mentioned, the idea behind this is to combine the strengths of humans and machines. So humans are good at kind of abstract and creative thinking. Humans are good at coming up with new ideas. But we are really not good at picking the best out of a million similar ideas. Machines are much better at it. So it's much better for us to create a million features and give all of them to a machine and let the machine pick the best, rather than for us to create just a single feature, because it will probably not be the best out of this million. Okay. So this is one way in which you can kind of make sure that you give enough freedom to the machine learning algorithm. You give it enough features to pick the one which is actually good for the particular data set that you are working with. The other challenge here is that we understand the domain quite well as humans, but we don't necessarily understand the specifics of a particular data set. And so we may know quite a bit about natural language processing, but we will not know really what is the difference between natural language processing in, for example, Wikipedia versus Twitter. There are obviously individual properties of those two corpuses, but we really don't have a good intuitive understanding of what those differences would be. So it's much better to let machine learning figure out those specifics based on the data. So if we try to kind of formalize it a little bit better, or maybe, the feature extraction is the idea of mapping raw data in whatever format it may be into a feature vector. And generally, this feature vector is some kind of d-dimensional, real valued metric space. So we are talking about, in whatever form our raw data is, it can be list of logs about the phone calls, it can be pixels in the image. We want to build a vector with d dimensions, each element being a number, And we want this vector to correspond to some kind of metric space. So we want features to be representations of our data, but in such a way that we can talk of them as points in real valued space. And of course, the idea is that the better features we have, the less smart machine learning can be. One extreme case would be if we can extract a single feature which is equal to the label that we are trying to learn, then machine learning is very, very easy. And so if we do this, then we can use any machine learning algorithm. It's guaranteed to find us the good solution. In general, we cannot go quite that far. So we want to find features which are closer to the target label than the raw data, but there will still be some work for machine learning to do. And the main reason why it's so important for this metric space is that machine learning is based on measuring similarity between objects. And in many cases, the natural data, the natural representation of the information that we have is not really in this kind of metric d-dimensional space. If you think of things like images or sounds or different time series data, they cannot easily be represented as points in metric space, even though technically in a computer everything is a number. So you can think of anything you can put in a computer, you can represent this as a very big number. So you could imagine that everything is actually in d-dimensional real number space. But it's the metric part of it that's so important. And as I mentioned, all the machine learning algorithms are based on this concept of similarity between data points. The similarity can be expressed in different ways. If you compare support vector machines and decision trees, they look at the similarity between points differently, but all of them measure the similarity between points somehow. So you really want this similarity measure to correspond to the actual semantic information you have in your data. So one very easy example is if you pick better representation, it will really make it a lot easier for the algorithm. So just think of a concept such as a date. And you can have 8th of August, 9th of August, or 8th of August 2019. And so now you have here 3 dates. If you look at it from the perspective of machine, those dates only differ by a single character. So you could imagine that they are equally distant from each other, that there is one character which is different. But that's not really the case, because the first and second are 1 day apart, and the first and third are a year apart. So that makes a very big difference. And if you actually represent your dates as strings, as written here, it's going to be very difficult for a machine learning algorithm to understand why the difference between the first and second is so much smaller than the difference between the first and the third. So if instead you represent your date as some kind of seconds since some epoch or something like this, then the difference between first and second date will be much smaller than the difference between first and third date. And then it will be a lot easier for the algorithm to see why some sensor readings change much more or something like this. But even then, the second since epoch representation captures the absolute distance between dates, but it ignores a whole bunch of other interesting concepts. And for example, a lot of things depend on a day of a week. And day of a week is not captured in this kind of timestamp since epoch. So you might want to represent your dates in several different ways, so that depending on what exactly are you looking for, or what kind of properties of this date are important, it's easier for the machine learning algorithm to notice that two dates are similar because they are both a Monday, for example. Similarly, if we try to represent categories, like if you talk about colors, red, blue, white, you could say that, well, let's just pick numbers. Red will be 1, blue will be 2, white will be 3. But that's also not a good representation, because now red and blue are more similar than red and white. And in the abstract, that doesn't make a lot of sense. I mean, in some domains it might be, but if you don't have any particular reason, you would want to make sure that all the colors are equally distant. So, of course, depending on what kind of data you have, you can do some very basic transformation, like binarization or just discretization of the data. So you can take your continuous sensor readings or whatever, and just split it into some number of discrete values. You could do rescaling or recentering to make things kind of look nicer. If you have categorical data, you can use the concept of one-hot encoding. So basically, you replace a single categorical value with a set of binary features from which exactly one is true. So you have one feature for each possible value of your category. So here is the example of all the letters or all the endings that we had is an example of this one-hot encoding. And you have all the possible letters with which an email address can end. Only one of those will ever be true. All the rest will be 0. But that solves the problem I mentioned with the colors, for example, because now the distance between M and A is the same as the distance done between A and B, and so on. All of those distances, or all of the values, are equally distant. One kind of more philosophical, again, way of looking at this feature engineering is that if you think of it from the perspective of machine learning, you really want to start by extracting more features rather than less. And the main reason is that algorithms are a lot better at ignoring unnecessary features than adding features which are missing. So if you imagine we would want to do some kind of medical diagnosis, if you really want to be using machine learning for it, you want to start by getting as much information as possible. So you could have something like height and weight of the person and so on. You can measure body temperature, blood pressure, all of the other things that you can measure. You can look at the medical history, what the past diseases, and so on. You want to take all of this information and feed it into machine learning model, assuming that it will be able to identify the irrelevant information and ignore it. Then, of course, when you start fine-tuning, you might want to play with this and start removing unnecessary information. But as a general kind of rule of thumb, it's better to have too much rather than too little information. But then, at the same time, when you are adding new features, there are some potential issues that you would want to avoid. Generally, any kind of informative feature, any feature which is somewhat related to the concept you are trying to learn is useful. But there are some features that can make learning harder than necessary. So I will talk about non-monotonicity, saturation, and feature interactions a little bit now. And here you can think of, we've talked about a number of different classifiers. Here is one good example where neither of those three problems can really be handled by a linear classifier. So you think about more, or kind of starting from very simple classifiers to more complicated ones, those problems can be kind of deal breakers for the simplest ones. The more complicated a classifier is, the more likely it is to be able to handle those problems, But again, if you can avoid those problems, you will probably end up with a better solution. So it's something to keep in mind when you are creating new features. So one example is the non-monotonicity. So if you think about trying to do a medical diagnosis, one of the features you would want to have is body temperature. So clearly, it is useful for predicting whatever we want to call the health score. But there is a challenge with temperature. Namely, it's not really clear if high or low is better. Right? It actually turns out that both high and low body temperatures are bad. There is really kind of a perfect middle ground, and you want to be as close as possible to this middle ground. Any kind of extreme is difficult. And that's a problem which makes it harder to create good models. So if you imagine a decision tree, we want to make a node which will split the data based on the body temperature. In a perfect world, we would want to say that if body temperature is correct or normal, that's one side of the tree. If the temperature is not normal, that's the other side of the tree. But we cannot do this if we have just raw value of body temperature, because too low is bad, too high is bad. We cannot really make a nice split. If wherever we put the threshold, if we say temperature higher than 40 degrees goes to the left subtree, lower than 40 goes to the right subtree, we will notice that one of those, the lower than 40, that one will have a lot of, or it will have a mix of normal and abnormal temperature. So it will have a mix of healthy and unhealthy patients. So that's something that is not particularly good. We want to have nodes with high purity, with only one example of a class, but we cannot make this kind of decision based on a feature like temperature. So we will try to think about what are the possible solutions. We can transform the input. So instead of, for example, temperature, we could say our feature should be temperature minus 37 degrees squared. Now we actually have a feature that corresponds to how far the temperature is from the norm. And that makes it much easier to make decisions, because now we actually can have a node in a tree where we say, if the temperature is more than 3 degrees outside of the normal range, those patients will go to the left subtree. Those with normal temperature will go to the right subtree. Now, the challenge here is, of course, that we need to know what corresponds to normal temperature. Right? I mean, for people, it's simple. We know that 37 is the normal temperature. But in general, it might not be obvious what is the normal value for a particular feature. It actually might also not really be the case that 37 is the best possible parameter here. It might be that some other parameter would be better. So one way of looking at it is that we would want to, coming back to this concept of feature templates and kind of building blocks from which the classifier should be building the models. 37 seems like a very low-level detail, that the kind of example when I said we really, as humans, are not great at coming up with those numbers. Right? We don't know if the threshold here really should be 37 or 37 and a half or 38 or 36 or whatever. We would like to avoid having this decision. This is the kind of decision that we would like to let machine learning algorithms do. So one way of looking at it would be, we don't need to hard code this 37 number necessarily. What we can do is we can have as features temperature and temperature squared. And then the classifier can, by itself, come up with this formula, temperature squared minus 74 times temperature plus 1369, which actually corresponds to exactly the temperature minus 37 squared. But this one is a linear combination of the features. And most modern machine learning algorithms can quite easily create new linear combinations of features. Most of them cannot do nonlinear ones. So if we don't provide temperature square as feature, it will not be able to build this particular expression. But as long as all that's needed is a linear combination, many machine learning algorithms will work quite fine. Right? So we should really think of those features that we are providing as building blocks that machine learning algorithms will then combine into good models. But then the question is, how can we really make the best building blocks? So another potential problem is what is called saturation. So let's say we go to a different area. Now we want to do some marketing. We want to find products which we should propose to a customer based on whatever query they have given. Here, one example of useful feature would be the number of people who bought product X. The more people have bought product X, the more likely we are, or the more likely it is that we should be proposing this product to our customers. And here, we don't have this monotonicity problem. Here, clearly, the more people have bought the particular product, the more likely it is to be relevant for new customers. The problem here is, of course, that this relevance relation is clearly not linear. If we have two products, A and B, and one was bought by 100 customers, the other was bought by 1,000 customers, sure, B is more relevant, but it's not 10 times more relevant. Right? We shouldn't think of it as, well, now B is that much more relevant. And if we have just this n of x, the number of people, directly as a feature, this makes it difficult to build good models because weighting positive and negative clues becomes hard. In most cases, there will be for every particular product, there will be some factors which suggest, yes, this product is relevant, we should propose it. And then there will be some factors which say, well, this product is not relevant, we shouldn't propose it. But if those factors have greatly varying weights or greatly varying values, it makes it difficult to find the right balance. And you have three factors that say yes, three factors that say no. You need to find some kind of balance between them. If suddenly you have those kind of features which vary, one customer bought something, or 100 bought something, or 1,000 bought something, it becomes difficult to figure out how to combine them in a good way. So again, here there is a number of solutions. You can try to do some kind of smooth nonlinear transformation. So I mean, every engineer knows that if you have a lot of or large range of values, you can use logarithms, and then everything looks much nicer, right? So you can do logarithm, you can do a number of other transformations, kind of similar kind. Again, you can think of it as a template that can work. You can also do a non-smooth transformation, that there is not really or you don't have to limit yourselves to smooth transformations. So another approach that you could do is, instead of doing, for example, logarithm, would be to do some kind of discretization. So what you could say is that n is in some bin value, and those bins can be growing. So n can be either 0, or between 1 and 3, or between 4 and 10, 11 to 50, 50 to 200. And you could even give it names, like it could be nothing, small, medium, large. You can put quite a bit of expert knowledge or domain knowledge into coming up with those kinds of beans. One interesting thing here is that you can have either overlapping or non-overlapping beans. So you can say that n should be between 1 and 3, or you could say that you will have different features. One feature will say that n is smaller than 1, another will say smaller than 3, another will say smaller than 10. So here you would have an actual overlap between those features. That can also be useful. So it's something to think about. And the third kind of problem I wanted to talk about is about feature interactions. So if we go back to our health example, some more features that are interesting is, for example, weight and height. And the problem with those two features is that you cannot say that weight or height are individually related to health score. Neither of those, if you just look at it in isolation, will tell you pretty much anything about the health score. It's the relation between the two that's important. Right? So for a classifier, it will be difficult to capture this kind of relation. So for example, if you have a decision tree, it will try to approximate this relationship with a whole bunch of nodes which all look very similar, but it will probably not do a very good job at it. So instead, what you can do, if you know that you have features which are actually interacting in the sense of it's not individual features that are related to the problem at hand, but it's a combination of those, you can actually provide this good combination as a new feature. So in this particular case, what you can do is you can just Google ideal weight for height. You can get a whole bunch of different formulas. One example would be this one. The weight should be 52 plus some 1.9 times height minus 60. And then what you can do, again, coming back to our non-monotonicity example, because now here we are coming with the idea of, okay, so there is a particular perfect value or perfect function connecting those two. So what we can measure is, for a particular patient, what is the deviation from this ideal weight? Right? Again, you can do exactly the same thing as before. We take the weight minus this idealized weight squared, so that we have the monotonic value that tells us the deviation from it. This becomes quite a complicated formula, but again, instead of the formula itself, we can just add a number of features. If we have height squared, and height times weight, this feature that we want, this perfect formula, just becomes a linear combination of features that we have. So then we can actually let machine learning figure out what the numbers in this equation should be. Maybe in our data set, this is different. I mean, I would assume Robinson's ideal weight is for US, that the relation might be different for Sweden. So for our particular data set, we might want to leave more flexibility to the machine learning algorithm to figure out some of those aspects. So this is a kind of a general idea. If you want to combine different variables, you can do some simple things like adding, subtracting, multiplying. One interesting thing is you can think of dividing different variables as a way of scaling or normalizing. Right? So if you have different countries with GDP and population, the GDP per capita is an interesting feature that we know is relevant. So dividing different features is probably one of the more common ways in which we can talk about, we can think of adding new interesting features, because we know that we can think of it in terms of normalizing by different factors. But those are kind of simple examples when we've looked at it in terms of just kind of engineering features based on more or less our expert knowledge. There is also a possibility of doing multivariate combinations or different kinds of algorithmic combinations of features. So one popular example is to do something like PCA or factor analysis or clustering, where you basically run some kind of unsupervised algorithm which finds some kind of structure in the data, and then you try to learn a classification based on this particular structure. And there are some examples of this which are at least somewhat assumed to be domain independent, like PCA you can do in pretty much any domain. But you can also have a lot of different approaches that are domain specific. So for a particular type of data, you assume that a particular transformation is good or has been shown to be good in the past. So now I will go through a couple of examples of how you can do what kind of feature engineering is typically done in some example domains. This will obviously not be exhaustive. You could have a course or several courses on each of those things alone, but I'm just trying to give you an idea of what is possible. So one common type of data is, of course, time series. And so when you have over time different kind of measurements. And when you talk about time series, the most common approach to doing machine learning based on time series is to extract features from different windows over this time series and learn from that. And so obviously you can take your data, divide it into some periods, for example, 1 month, and then over each month, you can get some basic statistics, mean, median, variance, any kind of statistical information. You can summarize your time series data using those statistics, and you can use this to do classification. You can alternatively do piecewise linear segmentation. So, for example, you look for trends in the data, and then you say there is a trend of going down, and then it goes up, and then goes down again. So you kind of smooth out a lot of noise in the data, and you get the general trend. And then each of those segments in turn you can describe using different features. And it can be both the features like the length of the segment or the slope of the segment, but also it can be the variability of data within this segment and so on. And then the kind of third big possibility is symbolization of the data. So you basically replace your time series data with different kind of symbols, and then you can do analysis based on the symbols, based on the simplified form of the data. A different approach towards time series is, of course, to do something like Fourier transform. I don't think I need to go into details of what Fourier transform is, but the basic idea.
Just a short question on the last slide.
Yep.
Isn't symbolization the same as discretization, or no? What's the difference?
It can be. So symbolization is one way of doing discretization. It's basically kind of different communities that talk about those things. So it's not entirely obvious how it really how those two things compare.
Mm-hmm.
But in a sense, yes, they are quite similar. It mostly depends on what is your next step after you do symbolization.
Okay.
Because if you do discretization, the kind of main idea is to either abstract away the noise or to compress the data. Those are kind of two main reasons for doing discretization.
Yeah.
When you do symbolization, you are mostly interested in the next step after it would be to find common patterns. So you would say that, for example, CBA is a common thing, that's something that happens often, and so on.
I see.
But in a sense, they are pretty much the same because you end up with discrete number of symbols, whether you call them ABC or 1, 2, 3, doesn't really matter.
Thank you.
Yeah, so Fourier transform is of course based on the finding common or dominant frequencies in the data. So instead of looking at the data as how it changes over time, you try to figure out what are the patterns that repeat themselves when you start thinking of the signal as a cyclical signal. And I will not go into details because I think it's quite well known. Another idea which is somewhat related to Fourier transform, but also slightly different, is the concept of wavelets. And the basic idea behind wavelets is that Fourier transform assumes that the signal is stationary, it's cyclical and always does the same thing, which is not really true in many cases, because in many cases the signal changes over time and you would want to find this changes over time. So wavelets is the idea of kind of extending the Fourier idea towards a whole family of functions that you want to find over time. So what you are basically doing is you are looking at a particular function, how well it fits your signal at different time points and at different scales. So you have the wavelet and then you scale it differently, you try to match it to your signal, and then what you end up with is basically a two-dimensional kind of picture which tells you how well different scales of this wavelet match your signal at different time points. So this goes, again, kind of a level beyond in terms of making a lot more features than that the machine learning can later look at. If we think specifically about speech, for example, this is obviously, on one hand, speech is a time series signal. This is just sound over time. But it's also kind of a specific signal in a sense that has particular semantics and it has particular features. So there are features designed specifically for speech signals. So one example is Mel-Cepstral features, which are based on the Fourier transformation of the speech signal, but then combined with post-processing, which is based on the actual properties of human auditory system. So it's not only based on the signal itself, but it's also based on how we as people actually perceive this kind of signal. So here is another example of more domain knowledge being added in order to make those features even more useful. A kind of similar thing happens when you look at images. So for images, of course, the baseline is raw pixels. So you have a representation like this. Then you can kind of summarize the image as, for example, histograms. So you can do histograms of different colors and so on. And then people have spent quite a bit of time trying to design different kind of features. So one example of kind of general purpose image processing features would be SIFT feature, which are pretty much the different orientations of image around particular points. So the idea is that for any particular point, you would measure those kinds of features, and then you would identify good landmarks or kind of characteristic parts of the image that you can represent in a particular way based on the gradients of those images. So you get those what is called key point descriptors. So you identify the interesting points, the ones which are actually representative of the information in the image. And then what you can do is you can match those points, for example, across images. So you can see that you have the same book in two different orientations by matching those kinds of representations. And I'm not going into details here. Another example is the GIST descriptors, which are descriptors of the complete scene based on the edge orientation in the image. So again, those are based on the pixels. You can actually compute those kinds of features, and they are better input for things like object detection and so on than raw pixels, because they better correspond to the specific properties of interest in the images. In text, for example, one of the popular representations is bag of words, which is basically just how often a particular word occurs in a text. And on one level, it seems very, very basic and maybe even stupid, because we all know that the order of words in a text matters quite a bit. But turns out that for a lot of tasks, it's not that important. We have so many different words that just looking at their frequency is enough. Obviously not for all the tasks, because this only works for texts which are long enough. Like if you have a single sentence, then of course the frequency of the words wouldn't be informative enough. But you can do surprisingly much just by looking at the frequency of words. At the same time, you can also look at the text from the kind of opposite perspective, when you say you don't care about all the text, you only care about the n-grams, so the sequences of words, so all the pairs of words, for example. And you can look at single words, pairs of words, triplets of words, and so on. So here, if you look at Pride and Prejudice, you can get the frequencies of different pairs and triplets of words. And this actually turns out to be quite informative as well. You can do not very, or quite good prediction or spell checking as well, based on the n-grams. You can use n-grams to track changes in usage or in semantics over time. Here is quite interesting plot that shows how the frequency of United States as plural versus United States as singular have changed over time. I think it's quite interesting. Basically, nobody talks about United States as plural anymore, but at the beginning, that was the common usage. And you can also do quite a bit of this, for example, for sentiment scoring. So for figuring out if a particular statement is positive or negative, turns out you can do this by looking at different digrams. For example, never liked or no trouble are quite informative in terms of whether somebody is, for example, review is positive or negative. One of the challenges with digrams is that some of the words are generally or inherently more common than others. So you need to be a little bit careful about what you are actually comparing. So one feature which tries to go beyond that is called TF-IDF, time frequency inverse document frequency, which basically combines the frequency of a term in a particular document versus its frequency in the rest of the corpus. So This you can use in order to identify the actual differences or the most informative words in different contexts. So here is quite a funny thing that if you look at the State of the Union addresses of different presidents, here is the ranking of the words which are most informative for this particular president compared to all the other presidents. And so it turns out that Washington was talking a lot about Indians, and nobody after, well, neither Obama nor Bush are talking about Indians all that much. So there are some quite simple features, if you think of it, which actually, if you use them, can give you quite nice information in the end. Those were kind of features which were designed based on expert knowledge or domain knowledge, kind of by hand. Especially recently, with the growth of deep learning, there is actually quite a bit of work on automatically designing features. So one example of this other direction is what is called semantic embeddings. So I will talk a little bit about the word-to-vec approach, where basically the idea here is to put the words in a space such that you can actually do mathematical operations on them. And one cool thing that those kinds of approaches can do is they can say, well, if you take the representation of man and you subtract the representation of king and you add the representation of woman, you will actually end up with the representation of queen. So basically the idea is that you want to represent the words in such a way that there is a certain type of relation that corresponds to some kind of semantic meaning. So for example, you would want to have the relation between a country and the capital of this country be represented by a particular vector, and some other relation be represented by another vector. I will not go into details of how this is calculated, but basically the idea here is to do a prediction based on a context of a word. So in this particular case, what you want to do is you want to predict the word mat based on the sentence before it. And of course, this particular prediction will not be very good because the cat can sit on a lot of different things. So the classifier can never reach high accuracy. But that's not really the point. The point is to find commonalities between words based on the context in which they appear. So it turns out that the capitals and countries often appear in similar context. You can take a sentence and replace one country with another, and the sentence will still make sense. It will make a lot more sense than if you replace the country with a person's name, for example. So this is the kind of relationship that this kind of network is trying to learn, and actually does quite well in some cases at least. So you can use this to build features corresponding to individual words that will capture some of this semantic information. And that kind of approaches you can use also. You can do this beyond just text. So there is a method called med2vec, which uses similar technique in order to analyze medical information. Right? So the basic idea is, okay, if you look at all the medical journals information, what can you learn? And you can actually learn different relations between diseases and different relations between medications, which are interesting, based on the demographic information of patients and the historical visits information of those patients. And those kinds of approaches are basically all somewhat based on the unsupervised learning idea with the concept of you want to look at a lot of available data without the labels, because labels are expensive, but in a lot of domains, there is a lot of data, raw data, which is not necessarily labeled. So you want to find ways of building features, useful features, based on just unlabeled data. And one general concept of doing this is called autoencoder, which is the idea of you want to build pretty much compression of the data by trying to take the data and predict exactly the same or similar data, but putting some kind of a bottleneck in the middle. So this is a representation of a neural network where you have a long input at the beginning and you are trying to reconstruct the same long output at the end, but there is a bottleneck, a small amount of information somewhere in the middle. So the network first needs to compress the initial input into something small and then reconstruct it as well as possible from this small representation. And then this code in the middle can be used as features. Turns out that it works quite well in several different settings, and you can do it in different ways. One approach is what is called noisy autoencoders, where you are trying to you feed them with noisy data, you compress it into some representation, and then you try to reconstruct the denoised image, so image without the noise. Or you can do it in kind of 3D setting when you are trying to present the network with an image from one point of view, and you kind of request it to reconstruct a different point of view of the same image. There are some interesting results in this. And the basic idea is that the kind of point behind the success of deep learning is that it's trying to do what is called end-to-end learning. So what I have mostly been talking about in this lecture was the classical learning, where as opposed to deep learning. So in classical learning, we have our initial data, let's say an image. Then we do this feature extractions or feature engineering, where we come up with a lot of different useful ways of representing this image. And then we feed those features into a classification. And if the classification makes a mistake, then we try to redo the classification to say, no, this is actually not a dog, it's a cat. But we keep the features the same because the features is where we have put a lot of effort into. Deep learning instead is trying to learn the whole process. So this is why it's called end-to-end. It doesn't have this feature extraction, the manual feature extraction at the beginning. It's trying to take the original raw data and learn hierarchical representations directly from the raw data. And the challenge here is, with enough data, it works quite well, but you really need a lot of data. At the beginning, when the amount of data you have is not very big, it doesn't work. You really need quite a bit of computational effort and quite a bit of data before those kinds of blind, in a sense, end-to-end learning can work without taking into account or taking advantage of the features based on domain knowledge that people have provided. So here are the kind of examples of hierarchical features that the neural network will be detecting. So in the first layers, it will detect simple things like lines and corners, and it will basically build more and more complicated features based on those as you get farther into the network itself. The basic idea behind all of those things is, of course, the generalization of machine learning. So you want to build models which will generalize well. And different data types come with different challenges. So you want to build good features that will make it as easy as possible to generalize well. And one of the challenges here is also making sure that there is no information leakage from the test set back to the train set. So when we talk about generalization in machine learning, we say we train on some data set and then we evaluate on a data which was not seen before. But this can be sometimes challenging in case of, for example, time series data. If you are not careful with splitting the data, you can end up with some information from your test set already being visible in the train set. I will not go into details of cross-validation again, but you basically really want to make sure that when you are working with time series data, you always train on a data which goes before your testing data. Right? So when you want to do cross-validation, you kind of need to get longer and longer periods of training data and always test on the data that comes afterwards. But it's not entirely easy in many cases, because this kind of information leakage is very common, and it can happen in many settings where you design your machine learning algorithm and you do some estimation of the accuracy, and then it turns out that after deployment the accuracy is a lot worse because during your experiments you have actually taken advantage of some of the information that you shouldn't have, so some information that you will not have access to in the deployment. So the easiest way to track those kinds of things is probably in competitions. So for example, the most classic example of this was one of the early competitions about predicting stock market prices, where the setting was that the training data was different kind of companies, and then the testing was done on a subset of those companies. And the companies were removed from the training data at different time points. So basically, for the test data, you would not have information about this particular company after the target prediction date, but you would still have information about other companies. And it turns out that wasn't a very good idea, because if you want to predict stock market, doesn't really matter. The company doesn't matter so much as the overall kind of the average price on the stock market. Basically, if stocks go up, almost all go up. If stocks go down, almost all go down. So if you know how the rest of the companies are behaving, it's a very good predictor for how a particular company will behave. So this is one example of this kind of leak. But you can do it in a number of different ways. So you can also get this kind of leakage by getting different information sources. So if you want to classify, for example, photos into cat versus not cat, it might be useful, or you might end up learning actually based on page title, not based on the image contents and things like that. So in the ICML, one of the challenges, there was actually quite a bit of this kind of leakage as well. So this was a challenge about predicting whale mating sounds, or detecting whale mating sound, basically if a sound contains whale or not. It turns out that by looking at the length of the file and the timestamp embedded in a file name and the order of the clips, it was possible to get close to 90 or over 99% accuracy. And so here is another kind of those examples where the data preparation really wasn't really good enough, in the sense of there was different, you could see the difference in processing of files which were actually really headways and the ones which are artificially added to make things harder in the competition. The other side of this, in a sense, is the bias in the data, because one case is when there is a leak of information in terms of you have some data that you shouldn't have access to because of how the experiment was set. The other side of it is if you actually sample your data for your training in a different or incorrect way. Basically, if the test and deployment inputs have different distributions, and it's well known that it's very, very difficult to get data which is exactly representative. There are many settings in which you have some level of sample bias where the data that you are using for training does not really correspond perfectly to the data that you use for testing. And another potential reason for this is also the non-stationarity, when whatever you are trying to model actually changes over time. So you collect some data now, you build a model based on this data, and then you deploy it. But by the time you have deployed the model, the underlying distribution might have shifted at least a little bit. So what you are seeing, your model doesn't behave as well as you expected, because it was trained on a different kind of data than what you are seeing right now. And that's one of the also common challenges. Okay, and that's more or less what I wanted to talk about today. Any questions?
Are these feature extracting basics the same, independent of what kind of machine learning algorithm you would like to use? Or do you have to consider the machine algorithm to be used?
So the basics are pretty much the same. Of course, there are differences based on the algorithm. So if you know what kind of algorithm you want to be using, you can try to come up with features which are better for this specific algorithm. But generally, I would say it's better to do the other way around. So to try to come up with the best possible features you can, and then try a whole bunch of different algorithms and see if your features actually work better with one of those. Just because it takes a lot more effort to come up with features. Once you have your features, you can run all the algorithms and see how they behave.
How much data do you need before you can start using deep learning?
As a general rule, too much.
Too much, okay.
Well, the problem is there are very few success stories with deep learning. The ones that we have are great, but it's pretty much only images, text, and speech. And the reason is those are the only really big data sets that we have. Right? I mean, we have gotten those success stories when we've started having millions of cat photos, Instagram, YouTube. This is where the amount of data that you really need in order to do something from scratch with deep learning. There are some attempts to kind of do some form of transfer learning with deep learning. So where you learn on some domains in which you have a lot of data and then you try to adapt it to something else. But there are mixed results with those. But as a general rule, it's not easy to use deep learning in kind of any other or any new domain.
Okay, yeah, that's pretty interesting. I mean, a lot of people are talking about it, and it seems very hyped at the moment. So I thought it was more used, so to speak.
Well, it is very heavily used in those three domains. And to be honest, those three domains correspond to a lot of what is being done. But it's still far from kind of the default solution, even though, yes, everybody is talking about it and everybody wants to try a little bit at least.
Yeah.
Okay, great. Well, thank you for today.
Thank you.
Yeah, thanks a lot. It was very interesting.